So today, guys, we're going to look at the Gravitational Interactive via Physics classroom. So the purpose of this is to investigate the variables that affect gravitational force between a planet and its moon. So procedure here, a planet and its moons, or moon, are shown in this picture below. Now, via the simulation, they want us to click and drag the moon to various positions around the planet and observe the gravitational force vector. Then, in the diagram below, draw a force vector, which is an arrow with an arrow head, to depict the direction and relative magnitude of force acting upon the moon and the designated locations. Note the size of the arrow should be representative of the strength of the force. So we got like a couple spaced out things here. So let's say we do the far top one. You see that it's got only a very, very small arrow, and it's pointing towards from the direction of the center of the moon towards the planet. So we could go to shapes, insert line. I'm going to go to black here, do my best, and I'm just going to make a very small arrow. That's close. All right, what else we got? We have this guy, so it's going to be technically should be even smaller because it's farther away, but it should still be pointing towards it. Now, as you get closer, what we should see is the length or the magnitude of the arrow gets bigger. And no matter where we drag it, okay, it's always going to be pointing towards the moon. I'm sorry, towards the planet. And why? Well, gravitational forces are attractive forces. So we got close ones, you got a very big vector going. So the closer they are, they got a very large vector going on. It shows it like almost going through the planet. I'm not going to go into that crazy a detail. The idea is so you can see or get to the understanding that the closer these things are to each other, the greater the gravitational force appears to be via the vector. Just from showing the vector here. Okay, as we get farther away, they get smaller. So we're just going to add a couple of arrows. This one's going to be pretty small. Doesn't have to be, perfect here, guys. But try and make it kind of come from the center of the planet towards that guy. Okay. Now, from here, is the relationship between the gravitational force and distance of separation, so the distance between the moon and the planet, an inverse or direct relationship? Okay. So what does an inverse relationship do? As one factor increases, the other decreases. So let's see. If we decrease the distance between them, what happens to the force vector? Holy crap, it got a lot bigger. Okay. So if the distance between them decreases, the force between them increases. So then let's say if I separate them and I start to move them away from each other, so I increase the distance, what happens to the force? It decreases. So that would be an inverse relationship. That would be an inverse kind of relationship. And explain the evidence for your conclusion. So basically what you're going to want to say is by moving the moon to various locations, you can see that the closer you get, the larger the force vector is, and the farther away you get, the smaller it gets. So you guys will type something in like that. Now, it wants us to note that the simulation allows you to display the force of the smaller moon pulling upon the larger planet. Now, click the tap button to show the force acting upon the planet. Which force is largest? The force on the smaller moon or the force on the larger planet. Okay, so let's click this and see. A little difficult to tell, but I think that looks pretty close to me. So I can grab this little ruler and move that. So what I want to do is I want to get it to a distance where the moon, if I go from the center of the arrow, it's going to match up right here with this first line. So I want to go farther away. And about like that. So like the part of this ruler matches up here, and it meets right as the arrowhead clicks. Now I'm going to slide this over. Damn it, can't do that. Actually, I can, because that's like one full unit. That would be like doing this. All right, so it's like the back here matches up just like that. So they happen to be same magnitude. Now let's see real quick if I just decided to go farther apart. Yeah, they seem to be, yeah, same size. Okay. So I would say that they happen to um, apply the same force on each other. I would say it's something like that. They're the same magnitude. All right, so now we got to drag the moon to various locations in order to determine the quantitative. So the quantitative, we want some numbers now. So we want to see the effect of the distance on this gravitational force. So we're going to examine the effect of doubling, tripling, quadrupling the distance of separation as measured from the planet's centers. So consider the planet's surface to be a distance of one Earth's radius, one R planet. Use the table at the right to record data for whole number multiples of R. So how we're going to set that up? Move the moon all the way over until we looks like we can get its center to match up with one of these, with this far blue line over here. That's not a straight line, but that's not a rocket. Okay, you know what I'm trying to say. The blue line. All right, so the center of the planet is in line with that blue piece there. Now we can drag the moon and move it so that it's one distance away. So what does that mean? I want the, let's see, the center of the Earth to match up with each one of the following guys. So actually, let's put it here. And let's just count for a second. Okay, we got 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Okay, so we're going to use this all the way up here to 12 because they ask us to go to 12R. So I'm going to match the center of the Earth with each one of those dots, essentially. And then we're going to record these values. So let me get my eraser out. Okay, and let's try and get it centered up as best as we can. All right, the force I'm getting here is 302.6 newtons. I'm probably going to zoom in for you guys. Okay. I'm sorry. Hold the phone. That would be, I guess, the base. No, can't do that. So this is, some of the things that we do and we mess around with, and the reason why we cannot do that. Okay. All right. So my mistake was, and it's a good thing I caught it. So the reason why we couldn't have the numbers here, and is pretty much because we have to go from the center of Earth's radius to the center of the moon. Now, if we started here as the center, then this would be considered just the one distance. And so to double, we would need to do this, and we wouldn't have enough data points. So we are going to need to erase these real quick. Let's drag the Earth. It may not like let you click on it at first. It may stop you here. Then you gotta let go and click again, so that it's measured. Boom. So it's the Earth or this planet, whatever, should fit right in between two of these things. So we want the center of this guy. So this would be 1. This guy here would be 2. We would essentially double the distance, because that's what they wanted us to start on here in this graph. 3, etc. 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so this looks like it's good. It's pretty snug in here. Let's see. Let's move the moon so we get it like kind of like centered like this, so that it looks like it's centered in between this whole little crosshair. So I'm gonna make my dot here. Drag the Earth. Click. Okay, and this big guy should fit snug in between all of this. So it looks like we're at essentially this. Okay, 1072 should be our baseline. So I'm just gonna write that up here. Now, geez, sorry about that, guys. Now we can double the distance. So to the next line over. And now we're at, now it looks like we are at 284.5. Now triple the original distance. If it's off by a tiny bit, it's okay. It's kind of hard to get it to fit exactly perfect. Okay, I got this one here is 129. Four times the original. 73.3. 5 times. 47.8. 6 times. 32.9. Next one. 7 times. 24.5. 18.6-ish. 9. 14.7. 10. Approximately 12 newtons. 11. 9.9. Approximately, give or take. All right, again, they're not all going to be 100% perfect with each other, but close-ish. And 12. 8.3. Okay, so here are our values. All right. Now, if the separation distance between the moon and the planet is increased by a factor of 2, then the force of gravity is blank by a factor of what? So, guys, actually, after just taking a look at some of the numbers and crunching them out, I'm going to wind up switching, I guess, my original force to this number here, 1138.5, just because I didn't have this thing quite like fully centered. So you should be somewhere around probably closer to this guy here. All right, this 1138. Somewhere in between like 1138 and this 1210, somewhere in between there for your starting value. Okay, then get it centered. All right, so these values should be roughly the same though. 134.5, around 129. They should be very, very, very close. Now, as you basically take this and you're starting to divide out by these numbers, you should start to kind of see somewhat of a pattern. So what I'm doing is I'm just going to take my original value of this guy here, this 1138, and I'm going to divide it by this 284.5. And that comes out exactly to 4. But technically, it should be the new force by the original. So if we did 284.5 divided by 1138, it's going to come out to be 0.25. So, and that should make sense because as we got farther away, guys, look what happens to the arrows. They decrease. It decreased by a factor of 4 off that first one. So when you increase the distance, the gravity is going to decrease by a factor of what? So to figure out this number here, divide by or by a factor of, you can take the original, divide it by what you guys record. So if your numbers are slightly different than mine, that's okay. So 1138 divided by the 284 by a factor of 4. And then the next guy, 1138 divided by 129 is about 8.82. So again, this is a decrease by a factor of, let's see, 8.82. And let's take a look at the next one. And we go 4 times. So 1138 divided by 73.3 is about 15.5. Now, for the time being, let's just say we're going to round these up. This would round up to what? Approximately 9. And then this would round up to approximately, I don't have an approximate symbol right now, so I'm just going to use this, 16. So think about this. 2, 3, 4. 4, 9, 16. What does that have in common? How are those related? Good. 2 squared, 4. 3 squared, 9. 4 squared, 16. Now, granted, they're off slightly here, but it's pretty good for, all right, any kind of experiment to be that close. I mean, you should be relatively close. If you're way off, then we're probably moving things a little bit too far, or we didn't start them close enough in the beginning. So number 5, now investigate the effect of varying masses upon the gravitational force between the moon and planet. Use the sliders to alter the masses and observe the effect upon the force. Use your observations to answer the following statements. Okay, so if the mass of a moon is increased by 2, increased by 3, increased by 2, increased by 3, decreased. Okay, so they tried tricking us. So because the sliders have different different things where they close out. Like you can't go any lower than 5, you can't go any higher than 50. So to get everything perfect, it's going to be a pain in the butt. So what I decided to do is start off and call 15 our starting number. All right, and we got 164.5. So I'm just going to kind of jot this number down. Okay, so when I increase the mass of the moon by 2, what's going to happen? So what's 2 times that? Maybe 30. And now I'm at 329.2. So what we can do is 329.2, and we can divide it by the 164.5, and that comes out to be 2.0012 and change. So yeah, we increased mass by 2, the gravitational force increased to this number here. So it increased, and by a factor of 2. 2.00 and change. So that's very good. Okay, now let's go from that 15 times 10 to the 22nd to, if we doubled it, it was 30. So triple of 15 would be 45. So at 45, we're at 492.9. Just going to kind of run it underneath here. 492.9. Is that what it was? 492.9. Okay. So I'm going to take this and divide it by the original number. So 492.9 divided by 164.5. And that comes out to be 2.996. So again, it's increased. And now by a factor of 2.999, which is 3. Okay, that's good. Now we have to decrease it by a factor of 4. So we couldn't really go and use our guy from before that's at 15. So I'm going to go to 20. Because if I decrease that by 4, 20 divided by 4 is 5. So let's see where we're at here. We're at 218.6. That's going to be my starter. 218.6. 218.6. Now, if I decrease it by 4, so I drop this down to 5 kilograms. Oh boy. I'm at 54.8. So let's go here, 54.8. And I'm going to do 218.6 divided by that number. And what does that come out to be? Nope, I'm sorry, I'm supposed to take this number. I guess I could technically. This guy over this guy comes out to be 3.99. So look, it was originally this, it got to this. So did it decrease? Yes, it decreased. By a factor of, well, this number is 3.989 and change times smaller, so it decreased by a factor of 4. So let's discuss some data. Oh, I guess we can. Essentially, these are our data values by which you explain the logic behind our answers here from part A to C. So we set it at 15 to the 22nd kilograms. We doubled it to 30. We got this value. Divided out, figured out it's a factor of 2. Kept the original value of that 15, then changed it to 45 times 10 to the 22nd kilograms, divided by it, got a factor of pretty much 2.99 and change. So yeah. And then this guy, we moved it to a number that we can divide by 4. So the lowest one was 20. Got that as our original, and this was our new guy. So the numbers decreased for sure by a factor of how much? About 4 times. Okay, if the mass of Earth is C step 4, increased by a factor of 2, then the F-grav is blank by a factor of. Okay, so increased, 4. Okay, so the same thing applies as what we just did with part 5. We want to double the mass of the planet, or Earth here. Increased by a factor of 2, increased by a factor of 3, because they want some evidence. So what we have to do is we have to go change this. It was originally at like 4 something, 478-ish. We have to move it so we can like double and triple it, because that's what they ask us to do in E and F. It goes up to 600 and only goes down to 200. So this is what we're going to have to say is our baseline. So if we kept the mass of the moon at this tiny value here, 22 kilograms, or 5 times 10 to the 22nd kilograms, then 200. Now, granted, these aren't the exact values, but for the purpose of just kind of investigating and seeing how these things change proportionally, we're going to do this. We're going to take the mass starting out as 200, and we're going to take our baseline basically of this force as 23 newtons. So I'm just going to say, okay, if we started out as 23 newtons, now let's double the mass of this planet. So double of that would be 400. Come on. And we get 45.9. And if you take 45.9 and divide it by 23, you're going to get 1.999. So yeah, we increased our value. So it increased by a factor of 2. Kind of looks similar. So let's see. Can you guess what it should probably about? Let's guess. This guy up here increased by approximately a factor of 3. So, well, let's just say 23 times 3 is approximately 69. Nice. So we got to then, let's just see. We should assume that if we make this up to 3 or 600 because that would be triple the original. It should be close to 69. And it is very, very close, 68.9 newtons. So divide that by 23, you're getting 2.9956. So again, this increased and by a factor of 3. 68.9 newtons. All right, now we're going to decrease it by a factor of 4. Okay. Now that's going to be a little bit of a problem, I think. Because if it goes to 200, it only goes up to 600. Let's just see something for a second. Does that affect? Nope. Well, this kind of is a little bit of a annoyance because we can't really change the mass of the planet anymore, right? The lowest thing we got is 200, and multiply that by 4 is 800. So that would mean we would have to start at 800 and work our way down to 200. But based on our patterns that we have kind of concluded from our data, all right, that should lead us to believe that by decreasing it by a factor of 4, that it should be decreased by a factor of 4. Just kind of like what we did here. When we increased the mass increased. You doubled it, it increased by a factor of 2. You increased it by a factor of 3, force increased by 3. You decreased it by 4, it decreased by 4. Again, different size for the planet instead of the moon. Doubled the mass, you doubled the force. Tripled the mass, you tripled the force. If you decrease it by 4, then it should decrease by a factor of 4. All right, and discuss some of the evidence, reasoning for which you explain the logic behind your answers. Again, we set it to a certain value, we doubled the mass, and we got a new value. All right, we divided out and we figured, okay, it's about double. It is about double our original. And we tripled it. It is about triple the original. The only one we can't necessarily show full evidence for is this guy because the sliders don't allow us to really make that jump. So just based off the pattern and data from the previous examples, yeah, we're going to say that this guy here decreased by a factor of 4. So do you need to write anything in? No, not necessarily. If you put in your numbers here, all right, whatever your numbers are, you should be fine. Okay, and now let's develop an equation. So if you had to develop an equation that is with a proportionality constant that describes the relationship between the gravitational force, F sub grav, or F sub g, the mass of the moon, mass of the planet, and the distance of separation between them. All right, then support the claim with the equation, with evidence and reasoning. Okay, so let me zoom out for a second. So things that we did. We changed the distance. We changed the distances here. And you can see that, yeah, it gets wicked small. So the farther away you get, the smaller the force gets. The closer you become, the larger the force becomes. So if these two things were like right basically on top of each other, you're looking at a much higher force than, if they were double the distance away from the original, etc. All right. So based off of the things that we had done, distance, what was going on? If we increased 1 by a factor of 2, it decreased by a factor of 4. We increased it by 3, it decreased by 3. Increased by 4, decreased by 9. And if we increase by 4, it decreased by about 16. So if we kind of continued on that pattern, that 1138 approximately, let's say 5 times, this 47.8. Okay, it's a little under 23. But the pattern should kind of hold that what we should be seeing is something here. These guys are squares of these, right? The 15 and a half, the 16 is square, 4 squared is this guy, 3 squared is the 9, 2 squared is the 4. But what happens as we increase the distance? What happens to the force? It decreases. So what that means is in an equation, F sub gravity equals, what that's going to tell me is that is going to be underneath this equation. That's because it's inversely what's going on. So when we have an equation, you can have, let's just say, I don't know, x up top and y on the bottom. These are just random numbers or letters for right now. Whatever happens up top is directly going to affect. If I double x, force would double. If I triple it, that would triple. This guy, if I doubled it, it would get cut in half. But what happened was when I doubled these guys down here, it went to 4. If I tripled it, it went to 9. So when I'm the bottom half of this equation is going to be the distance, because that's what we were talking about. And the distance was squared, because when we doubled it, that's basically saying divided by 2 times 2, right? Because it's squared, and that's 4. So it'd be 1/4. If d was a 3, 3 squared is 9. And what happened? We came out with approximately 1/9 the original force. If d became a 4, it'd be 1/16 the original force. Okay, so then what's good up top? What else did we do? We increased the mass of the moon, we increased the mass of the earth, and saw what happened. So those guys have directly proportional relationships. And because of that, you wind up with the fact that they are directly related, and so they're going to be on top of this equation. So we have the mass of moon, so sub moon times, let's do this. Nope, excuse you. Mass of the moon times mass of, where is this guy? M sub Earth, or planet. All right. Develop an equation with a proportionality constant. That describes the relationship. So there is a proportionality constant that gets multiplied by the 2 top values and then divided by the distance between their radius of the planets squared. Now let's see for 1 second. What do I want you guys to do with that? All right, so just after looking through some stuff, we're pretty much going to leave the equation as is. Now there is a proportionality constant that is involved here, which the value for that is, well, we're going to discuss in a little bit, but it is big G. So it's big G times mass of the 2 bodies in question divided by the distance between their radius squared is going to be how you can calculate the gravitational force that one object exerts on another.